everyone. Welcome to session 424. My name is Nil Kutlar. I'm an energy efficient building expert working as an architect at Center for Energy, Environment and Economy at Özyeğin University. I am holding a Master of Science degree in Architecture and Sustainable Environment from University of Kent, UK. And I have worked as a green building consultant and have been using BIM-Enabled tools and doing research to design energy-efficient buildings. Recently, I am running after the innovative ideas that can allow for achieving zero-energy buildings instead of near-zero energy ones. Although being not in the scope, living with COVID-19 pandemic perhaps makes this session more interesting, as digitalization has become extremely important across all sectors, and building information modeling is actually the digital representation of energy efficient and zero energy buildings. I think this situation promises that zero energy buildings, COVID-19, and building information modeling can be discussed together again sometime in the future. I have three distinctive speakers: Professor Salih Ofluoğlu, Associate Professor Sandeep Joshua Kora, and PhD Milad Ashouri. We will first start with Professor Salih Ofluoğlu, who is the head of the Department of Informatics at Mimar Sinan Fine Arts University, Istanbul, Turkey. He is also the professor in charge of Master of Science programs in Computer-Aided Art and Design and Architectural and Urban Informatics in the same department. He holds a Bachelor of Science degree in Architecture from Istanbul Technical University and Master of Science degree in Computer-Aided Architectural Design from Pennsylvania State University and a PhD degree in Architecture from Edinburgh University. His research interest lies in sustainable architectural design, performative design, geometric and building information modeling, integrated project delivery, and architectural design studios. He will be giving his presentation entitled BIM-Enabled Performative Design Education for Achieving Sustainable and High-Performance Buildings. Yes, Salih Hoca, the stage is yours.
Thank you for the introduction, Neil. I'm sharing my slides. Let's keep the fingers crossed. Can you see the slides now?
Not yet, but let's, yeah, I think it's coming up. Yes, go ahead, please.
Great. Hello and good afternoon from Istanbul. I hope you can hear and see me all right. Before I start, I wish everyone good health and positive thoughts during pandemic days. My name is Salih Ofluoğlu. I am a faculty member at Mimar Sinan Fine Arts University. The title of my presentation is BIM-Enabled Performative Design Education for Achieving Sustainable and High-Performance Buildings. In my presentation, I will focus on a teaching method for designing sustainable and high-performance buildings. We implement it in our Architectural and Urban Informatics Master's program. As we know, we have been experiencing an important environmental challenge called climate change. It is posing a serious threat to the future of humanity and our planet. We began to see its consequences as air pollution, extreme weather conditions, and loss in agricultural productivity in particular. Buildings are considered a major contributor to climate change because buildings still mainly use fossil-based energy. They create a high amount of carbon emissions. Many prestigious international events repeatedly emphasize the role of buildings in climate change. In order to combat this problem, there are also efforts regarding sustainable buildings, cities, and economies in the world and Turkey. EU has the 2050 energy strategy. The USA implements an initiative called Architecture 2030. There are also various green certification programs in the world that help creating sustainable buildings and neighborhoods. Here in Turkey, we have energy performance legislation introduced to promote energy efficiency in buildings. So where should we start to create sustainable buildings? To achieve sustainable and high-performance buildings, the design phase is critical. Good design can achieve good building performance, high occupant comfort, low operational cost. Unfortunately, architects and other building professionals have limited knowledge about sustainability. Their knowledge is general. They don't often take site-specific conditions, building topology-related issues, and climate data into consideration. One way of facilitating the design of sustainable buildings is the use of BIM, or Building Information Modeling. BIM is an effective project production and management platform used in AEC disciplines. BIM supports the idea of creating a realistic prototype of a building digitally. Unlike other modeling approaches, it integrates all graphical and non-graphical attributes of buildings. The non-graphical building attributes generally involve building physics-related data, such as thermal conductivity, fire resistance, sustainability classes, and cost of building elements. Since BIM reflects the real building conditions, it is also used in simulations for predicting the performance of buildings successfully. These simulations are calculated as building performance analysis. The most common building performance analyses are conducted for energy use, sun shadow studies, solar radiation gains, and wind effects on buildings. Using these simulations or analysis, design decisions can be tested and improved on a real time. The design approach that takes building performance into account is called Performative Design. It relies on general sustainability principles of buildings. It works with measurable data such as energy use intensity value or solar radiation gain kind of information. And it creates real-time responses. This allows instant feedback for design alternatives to improve. And we use building performance analysis tools to achieve a good performative design. Here I would like to talk about our teaching method that integrates building performance design. We have a postgraduate elective course that aims at facilitating the design of high-performance buildings using BIM-based simulations. The basic workflow is that when starting their projects, students set objectives for expected energy use intensity and the ratio of renewable energy use for their designs. They design and model their forms, conduct analysis on them, compare the energy use intensity they produced with benchmark tables, such as those of Ashouri's data and EPA, US Environmental Product Protection Agency. Based on that, they optimize their designs to reach their design objectives. The digital tools that we use in this course are Autodesk Revit and Formit for modeling, and Insight 360, Green Building Studio, Trimble Sapphire for building performance analysis. We also use flow design for wind analysis for the purpose. The course is focused on the early design phase. In this phase, high-level design decisions are taken, and these decisions set the stage for the following more detailed design phases. We work with basic geometrical models called mass models at this stage. These models typically include building type, climate data, site information, building geometry, wall window ratios. As I mentioned, we use Revit as a modeling tool. Revit also includes some referential data that support the process. For example, the building types is selected for the proposed design. All the spatial comfort, operation information, typical HVAC scenarios are taken into consideration. In addition, when the project location is defined, climate data for the region is automatically added to the model for simulations. This is a mass model. In BIM, a mass model is the least detailed, it's also called LOD 100, modeling type for creating conceptual volumes with surfaces. Students model their design alternatives along with surrounding buildings as mass models. It is important to include surrounding buildings because they affect the amount of shadows in the site that also influence solar radiation, wind flow, and energy use for the proposed building. Students examine the performance of their buildings under 4 scenarios. In this way, they isolate and understand their decisions more explicitly. They adjust software settings to include and exclude parameters that deal with these scenarios. The first scenario is the default mode, that is the direct output of the BIM software with general settings. The second scenario is the use of passive systems. It allows students to explore passive sustainability factors such as building material choices, wall window ratios, building orientation, etc. These are design-related and generally the least expensive design options. The third scenario integrates both passive and active systems. The active systems involve HVAC equipment, plug and load efficiency, and lighting factors. And the final scenario also adds PV panels for calculating solar radiation gains. Throughout the course, students are introduced different aspects of BIM-integrated building performance analysis and theoretical knowledge about sustainability in seminars. The first topic is about the use of energy in buildings. Students are introduced with basic information about heat transfer, thermal qualities of building elements, internal and external energy loads. The second topic of the course is sun and shadow studies. Here, solar access and shadow occurrence among buildings for the important days of the year, such as solstice and equinox times, are examined. The third topic is about solar radiation. Ways of calculating solar energy and PVs for design proposals are illustrated at this stage. Here, strategies allowing and preventing solar radiation are also explained. As the final topic, wind analysis is taken into consideration as an important sustainability factor. Students are shown how to produce wind analysis that is based on the simulation of air currents around the building site. The goal is to benefit from the air currents on the site and, if necessary, to avoid that. It is important that the proposed building at least does not worsen the existing wind patterns on the site. Here are some student works from the course. Typically, project starts with students' site analysis and sustainability objectives. At a minimum, students are expected to produce energy use results that are lower than ASHRAE benchmarks for the specific building type they recommend. As I mentioned, we also use other metrics, that is the energy used by building type table of the US Environmental Protection Agency. Students conduct energy analysis on design alternatives and make decisions to improve them for reducing the energy consumption of the building. The design that has the lowest EUI, which is energy use intensity value, qualifies for the other analysis works. The student conducts sun shadows analysis, solar radiation, and wind analysis, and improves his or her design by making design decisions. Here's the work of another student. You can see different design alternatives here. The student implemented different analysis work here as well. And she chose the one that qualified the best energy use values with the best energy use values. This slide shows the solar radiation analysis conducted on the building. There are other student works following the same procedures. They choose different building types and sites for their projects. The procedure requires to find the lowest energy using building forms and apply additional simulations on them to further improve it. I have to mention that sometimes we choose the second or third best alternative due to their better aesthetic qualities when the energy uses of alternatives were closer to each other. These are other examples, different design alternatives you can see. And another project, building information, building site information, and different designs and benchmark information available on the slide. And this one was a renovation project of an old building with addition proposals in a historic district. My final works is that what we learned from this experience is that by simulating the real-world conditions in the performative design framework, students made informed design decisions with measurable data and instant feedback, and they gained valuable insights regarding sustainable architectural design. That's all I want to say, and thank you for your attention.
Thank you, Professor Salih. Now we have our guest, Associate Professor Sandeep Joshua Kora from School of Architecture of Vellore Institute of Technology. He recently earned his PhD in architecture from Texas A&M University. He has a great penchant for teaching and research. His research mainly focuses on building energy and daylight modeling simulation and building information modeling. During his time at Texas A&M University, he had worked in two seminal research projects. These are ASHRAE 1468, which involved developing a standard for translating BIM data into energy models and physical building information modeling, and the National Science Foundation funded project in which he developed an architect-friendly prototype program for translating the BIM models to daylight models for performing daylight simulation in the early design stages. The paper, published as a part of the BPM project, has been featured as a key scientific article by Renewable Energy and Global Innovations, a website that showcases the research of exceptional importance to the energy industry. His presentation title is An Architect-Friendly BIM-Based Daylighting Simulation Tool for Designing Net Zero Buildings. Okay, Sandeep, please go ahead. Can you turn on your microphone, please?
Okay. Yes, thank you. Share screen. Can you see it? Can you see the screen?
Yes, definitely. Please go ahead.
It is showing the. Okay. Yeah. Thank you, Neil, and it is a pleasure to speak at this forum. And I want to thank the organizers for such a wonderful opportunity. And today I will be presenting a part of my PhD work as well as the work done in the National Science Foundation project. And the product of that research is the development of this tool. And my title is an architect-friendly BIM-based daylighting simulation tools for designing net zero buildings. And I'm an associate professor in College of Architecture, Vellore Institute of Technology. And I want to start with this verse. In the beginning, God said there was a light. Let there be light, and there was light. And one of the things, light is very important as it gives us the ability to perceive the world, both natural and man-made. And without light, we cannot see anything. And natural light is free, and artificial light is costly, both in terms of energy, money, as well as environment. So it is onus on us to design building which will use natural lighting. So in the world, countries use a lot of energy, and energy is created using fossil fuels. And in the last 2 decades, there is a tremendous use of energy in the building sector, and that is leading to the greenhouse gas emissions. And we all know global warming is happening, and also climate change is leading to the climate change. So the countries around the world formed an intergovernmental panel of climate change to address this issue, and they have given some recommendation. And we can see that in the last 2000 to 2010, the increase in the energy has increased by 2.2% per year. So it is expected that by 2040, the world energy will increase by 736 quads, and also there is a great need for reducing the energy consumption and also related greenhouse gases. And one of the main greenhouse gases is CO2, and which is generated by using coal. So IPCC has given some recommendation how we can do that. And one is replacing the use of coal in generation of power. Another one is creating energy efficient policies and developing design portfolio to reduce energy in the building sector. So I just want to talk about net zero buildings. Before that, we have a responsibility to reduce the energy in the buildings, and just to meet the recommendations by IPCC, we have to design buildings which consume low energy. Like there are several, like, for example, we see green buildings, high performance buildings, and net zero energy buildings is one of them. It could be a residential or a commercial building. It uses energy efficient measures to reduce its energy consumption. And whatever the extra energy it needs for its operation, it is supplied through renewable technologies. So that is the definition of net zero buildings. And in the buildings, artificial light consumes a lot of energy. It could be somewhere between from 25 to 40%, depends on the typology of the building. And daylighting is one of the best options. There are several, like Pacific Gas and Electrical Company said that daylighting is one of the opportunities that we can capitalize to reduce the energy consumption. And also effective daylighting is necessary to realize low carbon and low energy buildings. And we can use the daylight to replace fully of this 40% or a part of it, and depends on building typology also. And research also showed that by using daylighting in the buildings, the productivity and the mood increases rather than electrical lighting. And earlier, when projects were being designed, most of the building information is represented in either 2D or 3D form using the CAD tools. Later on, the technology has improved, and they were developing something called building product models and the building information models. Building models, the building information model contains like geometry, like wall information, window information, and relationship data, that is the wall as well as window. What is the relationship of these two elements? And also material data, like what are the thermophysical properties or reflectance values, and all these things are embedded in the BIM models. And also, according to Ash and Woodbury, since BIM authoring tools, we have Architec, Revit, and some other tools, custom developed tools. We can explore, it has a parametric modeling capability. If you could see this, by changing the parameter, you can change the shape of the wall itself. So we can use the BIM data, BIM authoring tools to study design alternatives and optimize the design. So net zero buildings, designing them definitely need building performance analysis. And some of building performance analysis are energy analysis and lighting in daylight and solar radiation and airflow, ventilation, and life cycle analysis. And while designing at the schematic stage, we had to run several performance simulation just to optimize design. Ideally, how in the previous, in the past times, they take the architecture model and they collect the geometry data as well as material data from Architec, and then they manually code that in building simulation software, and they run it. Suppose if this process is prone to errors, and it is also very time consuming. So if we have a building information model which has geometry data and material data, and since it has the parametric capabilities, and if we integrate building performance simulation tools such as Energy Plus or Radiance or some other tools, so we can study many alternates and come up with the optimized design. The prototype which was developed by us, it's named Revit to Radiance, and we have done an extensive literature search on what are the most accurate energy daylight simulation tools, and what we have also done an extensive literature search on comparative studies which reported on comparative analysis of different daylight simulation tools. What we have identified is there are two tools, daylight simulation tools, which are very accurate and very robust state-of-the-art tools. One is radiance, and the second one is radiance-based dacing. And as a part of project, we also looked into how the CAD models, which are used earlier, before the BIM really came into picture, are integrated with daylight simulation tools such as Superlight, Radiance, and Dacing. And these are some of the studies. And what we have inferred from this is, in every study, there was a custom program developed to integrate CAD and daylight simulation tools. And we also looked into whether there are any studies which have integrated BIM modeling tools with the daylight simulation tools. There were two studies which we identified. One was done by the Autodesk itself, and the BIM models are created using Revit, one of the BIM modeling tools, and they have used a custom plugin called FBX Converter, which convert that into 3ds Max, and they use 3ds Max daylighting model to do the analysis, and the results are produced. So one of the limitations of this process is that even though it is fairly easy and convenient to do the simulation, there are several manual steps which needs to be done and to check so that the daylight simulation is accurate. And compare it to Radiance and Dacim, 3ds Max daylighting model is not validated much. So it does a good job, but it is not validated. Whereas the Radiance and Dacim, they are used by academician researchers and students and all. The second research which we looked into is done by Stanford University, where they have used digital project, a BIM application tool, and they have developed custom plugins, and they have translated the data into Energy Plus and Radiance to do the thermal analysis, energy analysis, as well as daylighting analysis. However, the limitation of this is that the geometry for the Radiance daylight simulation has been taken from Energy Plus, which is not the real representation, true representation of real geometry, whatever the geometry which existed in digital project. So that is one of the limitations. So we, our literature review has also given us insight like BIM modeling tools are much better than CAD tools. Like CAD tools, when you are modeling the building elements, they are represented as a plane with no thickness, and they also doesn't have some material information embedded in them. It's just the geometry. And this is not a true representation. As you can see, the top images, there are just planes. So whereas the BIM, it models the elements with the thickness, and it's a true representation. It also has material information and the relationship information to which is needed for building to do the building performance simulation. So I just want to talk about Revit to Radiance prototype. So what we have done is we have taken Revit and we created a prototype a plugin which integrates Radiance and daylight simulation engines with in the Revit environment. And this is an Architect model. This is a simple model. We run the model through this prototype, and the prototype generates the results like images, the daylight values and false color images, and also annual daylight simulation values at the sensor points in the space. Before we developed the prototype, we also looked into some conventional method, whether we can convert the geometry and material data which is available in the Revit model to Radiance and Dacim input files. So Radiance comes with several utility programs which convert the CAD formats into Radiance formats. So we use the FBX converter. There are several paths which are explored, and FBX converted, and we converted into DWG format and the 3ds format, and then we converted that into using the Radiance utilities to Radiance format. However, we have found out that there are several limitations. Only geometry got translated, and the material information never got translated. And this path, the path 6, shows that Revit to Radiance plugin, and this is a one-step process. And this table shows different steps involved in each path. From path 1 to path 5, we can see that there are 5 steps and 4 steps. And the major disadvantage of this process is that if at all architects want to change the building, and he wanted to change the building 5 or 6 times, so 5 times into 5 steps, that is 30 steps, and we have to carry 30 steps to optimize the design. So it is not, it's a cumbersome process, and it is also error prone. Whereas this also showed that we require custom plugin to translate the Revit information to Radiance information. I think the screen got stuck. Yes, I'm here, but it's not moving.
Okay. Could you please wait for a second? Sandeep, you can actually tell to move the slides as you continue.
Oh, can you go to the next slide? I'm not able to see it here.
Okay, now we see it. Can you please showing the next slide?
Hello, can you hear me?
Okay. We do hear you.
Hello.
You can keep follow. Just a second, please.
Hello. Hello.
Do you hear us? You can keep speaking. We hear you. Sorry, just a few seconds. All right, we are having a little issue. I think we are going to move on to the next speaker, and then we will be back to Sandeep. Okay, now it's time for Milad Ashouri. And he is the senior data scientist at EnerZam in Canada. He did his PhD at Concordia University Department of Building, Civil and Environmental Engineering in application of artificial intelligence in building energy management. During his PhD, he modeled energy consumption relationships between appliances houses in a section of the city, using data analytics algorithms and made smart notifications in cases of energy wastage. He has a strong background in building HVAC systems, and control together with IT and programming. He is currently working closely with the software development team to create intelligent tools for a cloud-based data streaming, analytics, and visualization platform for institutional, commercial, and industrial building. His presentation is entitled Continuous Measurement and Verification, a Key for Energy-Efficient Projects. Yes, Milad, please go ahead.
Okay, just let me share my screen. Can you see my PowerPoint?
Okay. Yes, please go ahead.
So everything is good? Okay, well, thank you very much, first of all, from Zero Build Forum for having me on this forum. I am Milad, a data scientist at EnerZam Inc. and also a PhD. And today I'm going to talk about continuous measurement and verification for energy efficiency projects together with some data analytics that we are using in building automation systems. But let's first take a look at Canada's built environment. As you know, there are approximately 482,000 commercial and institutional buildings all across Canada, which are responsible for around 12% of total GHG emissions. We can add it up to 70% if we want to include the electricity generation also. So that shows a huge room for improvement if we want to reduce the GHG emissions and energy consumptions. But what makes us to invest in energy efficiency projects is obviously rising energy prices and also the cost benefits that come from a cleaner and lower energy consumptions. Also, there are a lot of incentives put by public financing and governments, which is part of their policy to reduce the energy consumption and reduce carbon emissions. But there are always problems in investing in energy efficiency projects. As you all know, not always actually energy savings that was promised before the implementation of the projects are equal to what actually is delivered. So we refer to it as risk and uncertainties that are involved in energy efficiency projects. Also, there are a lot of hidden costs that are not actually accounted for before the implementation projects. Therefore, the solution is a measurement and verification, what we refer to as M&V, which acts as an accounting system in any efficiency project, in energy efficiency projects. So what it does is it actually tracks the data before and after the implementation of the project and make sure the energy savings delivered is actually equal to what promised before. So it increases the certainty, it reduces the risks associated to the project, and also it can actually gives us some recommendations for the future activities and in order to actually improve the project. But let me just delve into M&V a little bit more, and let me explain how M&V actually works. So as you can see on this screen, we have two phases. We have before implementation of ECMs or energy conservation measures, and then we have a after period, which is actually the reporting period. So before this implementation period, we have a baseline energy profile of the building, which we measure. And then we have the implementation period, which actually we do not measure anything because the changes are happening and the building is in a transition mode. And thereafter, we have the measured profile, which is actually come from the actual energy, energy consumption of the building. But it's not, we cannot calculate the savings simply by, comparing the baseline energy and measured profile and then minus them. Why? Because there are a lot of parameters in a building, such as building characteristics, outside weather conditions, occupant presence, on all those parameters that are not equal in the baseline period and reporting period. That's why we need to actually come up with an estimation of a building energy consumption as if no implementation was done on the project. That's what we call adjusted baseline. And this is what we get by estimating the energy consumption of the building in the reporting period. Therefore, the difference between these two, as you can see here, energy saving is actually reported, and then we compare these energy saving to what actually was promised and was designed before implementation of the project. So this is a summary of MNV. So to summarize, MNV deliverables are verifying estimated energy savings. It is able to calculate also the GHG emissions reduction in efficiency projects. And also, by recording all the data during the project, it is able to inform recommendations for future implementation activities and to improve the overall process in case anything goes wrong. But there's always challenge to any M&V project. Unfortunately, at the moment in industrial commercial buildings, M&V is still a manual process. What it means is that we have to go to the site, get some data, and then clean the data, put them into Excel sheets, and start an analysis. So that means it is not scalable. By scalable, I mean any modification in the system. It means that we have to redo all these steps, update all the Excel sheets. So that is a weakness, obviously. And also the data that comes from the building are not in real time. Unfortunately, all the data that are being analyzed actually reflect the past behavior of the building. So it is not real time. So obviously we see a need for making this somehow more advanced and in real time. That's why we are in an era of smart building where we have sensor data, building automation system that are actually enabled us to do a remote site management, remote energy commissioning, and remote M&V. So it means that every energy analysis, optimization, fault detection on all those measures, energy conservation measures, are actually done remotely and in real time. That actually brings us a lot of savings, a lot of operational efficiency, and in case anything happens in the building, we'll actually spot them right in the real time, so we can take measures. But I want to talk about a little bit more about these smart buildings and big data in buildings. As you all know, the AMI, or Advanced Metering Infrastructure in commercial and industrial buildings right now, has led to the emergence of big data in buildings. So this vast amount of data, it actually should be automated and should be analyzed automatically, not processed manually. So there is no room for Excel sheets and manual analysis, as you all know, because of this huge amount of data. Therefore, we are actually starting to use some tools such as artificial intelligence or AI in building applications in order to analyze this data automatically and give us insights and information. So I want to talk about a little bit more about AI in building automation systems. As you see on this picture, we have a vast source of data coming from building sensors and the building management systems. So we collect and integrate all these data, clean them, normalize them from different BMS actually manufacturers, and then we analyze this data and then report. So the brain of our work is the analysis. Before delving into the analysis part, I want to mention that this is the only way of reducing energy consumption or reducing the GHG emissions without the need for replacing any equipment in the HVAC system or upgrading the reconstruction, or that actually costs us a lot of money. Therefore, by actually recording the data in real time and converting it into useful knowledge, we can find a lot of potentials to reduce the energy consumption, and that comes from our analysis part. So I want to talk about some AI use cases that we are actually doing at EnerZam as part of our analysis of the data. So what we do is we detect anomalies, power outages, and faults in real time. We also, it leads actually to the predictive maintenance. So the predictive maintenance is that by analyzing the data coming from an equipment, let's say boiler or chiller or equipment, we're able to detect any fault or abnormal behaviors before it actually happens. That actually saves us a lot of time and a lot of money. Therefore, this is actually a crucial task. Also, we have predicting energy consumption. As you know, predicting energy consumption has a lot of benefits. When a building knows ahead how much energy is going to use in advance, a day or a week before, so the building can get itself ready for actually responding to the demand. So the benefits are a lot. Also, we have optimizing the building control system in real time based on the predicting energy consumption. But I want to go a little bit further about how we do it and what are the actual algorithms behind all these analysis. So in fault detection, we have single variable approach and multivariable approach. Single variable approach means that we have actually a variable in a building. So we apply some time series analysis on that, and then we find all those times that the data shows some anomalous behavior as opposed to the normal behavior, and then we report based on its co-occurrence and duration. But as you know, a building HVAC system has a synergy effect. It means that whenever something goes wrong in a building, or whenever something is far from the design, it actually shows this behavior through a lot of variables, because all the variables are somehow interconnected. Therefore, the multi-variable approach is that choosing related variables. Let's talk about a boiler, for example. So what we do, we get instances of variables from a building, such as from a boiler, such as supply temperature, return temperature, and all those signals coming from a building, and then we find these correlations among them. Whenever this correlation is violated, we report based on their co-occurrence and duration and report to the building engineer. So I'm going to just delve into that a little bit more. We have automatic fault detection. As I said, here is a sequence of supply fan air status and command. And as you can see, actually common practice by a building engineer is to look at this data, graph them, and try to find the patterns that are actually weird as opposed to the normal behavior. As you can see here, we have some anomalies and abnormal behavior, but based on our analysis, we actually found out that we are able to do this automatically without the need for building engineers to look at this data. This is how we train some AI algorithms, and the AI algorithms are able to detect these anomalies automatically and report them to the building engineer. So this is the benefit that is coming from the automated fault detection and automated algorithms. So about the correlation analysis, as I talked about, we try to extract some correlations among the variables. And whenever, by looking at the records, whenever this correlation is actually violated, we report on them and we flag them as an anomaly. I want to give an example. This data on the left, as you can see, comes from the real building. There are a lot of data points coming from a BMS. We have around, based on the complexity of the building, it can be up to 20,000 points. So, for example, we have here condensate fan ampere, condensate mixer temperature, and all those chiller ampere, and all those data that come from the building. So we feed them, we feed these variables into our engine, and we try to find correlations among them. And whenever these correlations are actually violated, it means that something is happening in the data. For example, here, as you can see, these three variables, the air handling unit, return fan, and also cold deck temperature and mixer temperature, are actually dependent on each other. So by looking at the data, and whenever these correlation is violated, we flag on them. So for example, here, and you see an example of a detection of mixer temperature. So that shows that there's something going wrong in the boiler. So if we flag them and report them in a prioritized manner to the building engineer. But a very important aspect of our work, of analysis of work, is the feedback learning. So what we mean by feedback learning is that whenever we report to the building engineer sits in front of the computer and look at this data. So it tries to actually fine-tune the results, fine-tune our algorithm. So it is trying to teach our algorithm. Therefore, during an energy commissioning project or implementation project, so the algorithm, our actually engine, can actually learn the knowledge that comes from the building engineer. So at the end of the project, or at the end of a couple of projects, our engine gets smarter and smarter because it is actually learning from the facility manager or building engineer. That's what we call feedback learning. Just to give you an example here, for example, let's say we are analyzing some data. We are actually analyzing a variable in the building. So the user, the building engineer, can actually fine-tune this algorithm and try to ignore the false positive and actually fine-tune it. Therefore, in the future, anything that happens in a building which is similar to what has learned will be shown to the user, and not something that does not make sense. So that is the idea behind our actually feedback-based fault detection. But another area which we are working on is the forecasting. As you know, forecasting is actually a very important aspect in building data analysis. On the left side, you are seeing temperature, a rooming temperature, and also an algorithm that we have actually learned from these. The blue dots actually shows the predictions, and the black dots shows the real measured data. And you can see our algorithm is able to perfectly find the pattern of the data. Therefore, it has a lot of applications. For example, on the right side, you're seeing whenever this pattern is actually violated, and our algorithm shows that the temperature should go up, but it doesn't go up, it means that something has gone wrong in the building, and we report it to the building engineers. And remember that these algorithms are actually analyzing hundreds of thousands of data all at the same time. Therefore, the report is based on co-occurrence and duration. So holistically, it gives a lot of useful information to the building engineers. So up to now, there is no tool that is able to do a measurement and verification, fault detection, and prediction all at the same time in one place. That's why we at EnerZam are building a tool called Joule MNV, and MNV obviously comes from the measurement and verification. So what it does is it actually collects the data from the building management system along with the wireless sensors that are actually installed inside the building upon need. And then all these data are actually transferred to a box. We call it Joule box. So the box actually is able to communicate with the building manager system and sends all these data to a platform called Joule MNV. So in which we have our dashboards, we have our data stored in the cloud ready for the analysis. So I want to show you the deliveries of a Joule MNV and how actually it helps us. So what we do with this data is we analyze this data in real time through defining engineering calculations. I mean, key performance indicators of a building, baseline, set points, energy consumption indicators, energy efficiencies, and all those key performance of the building. And then engage the facility maintenance and operators team of a building with their equipment efficiency. Therefore, they see their equipment efficiency in real time in nice dashboards. Therefore, if anything goes wrong, they can actually be informed to prevent that in a timely manner. And also, our platform generates rich reports at the end of a month. Therefore, all the analysis done is sent to the maintenance team, also the building engineers, and we have the features of alerts, notification, informations, insights through in the knowledge coming from the building engine, and also the AI algorithm that actually analyze the data. So that is the value that we are bringing through our platform, the analysis of real-time data in building energy. So I'm just going to show you one example of this data. As you can see, all the key performance indicators of the building here are listed in groups. So the data are in real time and ready for the analysis. So thresholds, we apply the algorithms in order to make sure that these data are actually performing correctly. And in case anything happens, we actually are being notified. So that's actually very crucial, because in every energy project, unfortunately, the problem is that the traceability does not happen in the building. Therefore, by having this platform, we're able to trace in real time the data that comes from the building. That actually prevents a lot of damage, cost, and money. So to summarize my talk, M&V helps monitor the energy efficiency projects, as I said, before and after implementation project. And actually, this is a tool for capturing the energy savings and making sure that the results are actually equal to what's supposed to be. Joule is a great tool for energy utilities. It is good for energy efficiency contracts and basically any energy efficiency project that is going to be done. And we're actually in the process of putting 100 buildings under Joule platform until December. That means we have a large volume of data to build ML models, benchmark the energy baselines, detect anomalies, and all those behavior. So having such data coming from different buildings is a true value that actually we're looking for. Well, thank you very much for listening to me. And
thank you, Milad. It was a great presentation. I think we can continue to listen Sandeep again. Milad, could you please turn off your microphone?
I will start off where I have.
Yes, please.
Oh, are you? Is a single presentation that is the same, a single slide? Yes, I did.
Have you shared already? Okay, let's hold on for a second. We don't see the presentation. Okay. Just a second, please. Okay, perfect.
Are you seeing this two screens or a single screen?
Yes, right now we are increasing the screen. Just a second, please.
Hello, Neil.
Hello, yes. Are you sharing a split screen?
Yeah, I can. Are you able to see
Yes, now seeing it.
Okay,
yes,
great,
please go ahead.
Okay, sorry about that. My computer hung for some reason. Apologize for the inconvenience. Okay, so I left in the slide. I was talking about different paths that we have explored and mentioning that each path has 5 to 4 steps, and if you have to do multiple iterations, it would we have to run like 5 iterations into 5 steps, like 25 times. So it could lead to some errors in translation. So this exercise also showed us that there is a need for developing a custom plugin which would accomplish this translation of the Revit model into radians and DESIM input files and running the simulation in one click, which could be Architec friendly. So how we developed this? We developed this Revit to radians prototype using Revit API programming and C# language, and usually the Revit has we can create custom programs which are called add-ins in Revit language, and there were 4 programs which were created. What we have observed is Revit doesn't have some information which is required for the radians. So we had to create those parameters. So we created the parameter file creation. this first add-in programs handles that. And then the second program, adding material parameters, adds these parameters into for each material in the Revit database. So the parameters are added, if you can see here, like specularity and roughness, which is required by radiance material material description. And then we have to add the values. So what we have done is we have done extensive literature on the web and found out what could be the possible specularity values and roughness values for the Revit material database. And then we assemble that as a Excel file. And the third add-in program, reading material parameters, this will be there in the system. And once we run the third add-in program, all this information will be loaded into Revit project. And the final one is the model translators. Once the model is developed and the materials are added, and then the model translator translates the BIM model and run the simulation and generates the results. We can see here some pictures, radiance rendered pictures, as well as time series data and the illumination levels at the sensor point in the place. So the program, the model translator automatically takes the Revit information, material information, and writes to a radiance to radiance information, like how the radiance required the material information to be written. It automatically does. And we also need sensor point files for doing annual simulation using DASIM. So we have created a custom family, and you can see in this picture that there are 3 sensor points we have located, and then we also need sky descriptions in the radiance for radiance to create the images. So this information is found out in the view sun settings of the view in Revit. So we have access that information. The model translator takes this information and writes a radiance input file. One of the challenges that we have found out, which we had to address, is that Revit models the window panes as a solid blocks with a thickness, whereas the radiance need models the window pane as a plane surfaces with 0 thickness. So again, we came up with a method how to split it and convert that into planar, and the model translator does it automatically. Now we can run this add-in programs using external tool, which is available in a Revit interface. And this we have added the 4 programs, and sequentially we load them and we run them sequentially. And this could be converted into icons also. When we are developing a prototype, we just created the programs, but we can create icons for each program, each added program, and place it on the dashboard like we have this ribbons. So an architect can easily click that and get the simulation done once he creates the models. Once the model translator plugin is run, the Revit to Radiance prototype automatically launches the Radiance simulation, and after Radiance simulation, it launches the DASIM simulation, and the results are created. So these are the results, some of the results. And for any tool, we need to test the validity of how the whole process is happening. We have to validate the tool. So we have validated the prototype using 2 BIM models. One is an easy model and one is a bit complex model. So we are not validating, we haven't validated the radiance as well as DASIM because they are already validated and so much of literature is available. So what we are validating is we wanted to see whether the geometry information is accurately translated and the material information is accurately translated. So we have done a visual comparison. On the right, on the left, you can see a Revit model, a simple model. And on the right, the model translator created the input file, and Radiance have used that input file and created a view of the model. And this is the view generated by our view program of Radiance. We can see that they both are similar. And so with this, we could understand that the geometry, like the coordinate information, is accurately translated. And then we also tested how the material properties are being translated. So we took one material named Windows Sash from the material database of Revit, and we have taken the RDG properties of that, and then the specular properties which has been read from the spreadsheet. And we have done a hand calculation to find out the reflectance values from the RGB values, which is done using a brightness formula, which is available in Radiance manual. And the manually calculated value we have here 0.73. And we have opened the Radiance input file and looked at the material description in the input file. And we have found out that the material information is accurately translated. So in the whole process, we both material as well as geometry got translated. And in the second model, it's a fairly complex model. It is a solar decathlon model, Stanford solar decathlon model. And they have sent us this request. And so we used our prototype to simulate. And solar decathlon model is a net zero building which they were designing for a solar decathlon competition which happens in the US. As you can see in the plan, we have put the sensors in each room, and we have also created one camera which would generate. This camera information is taken by the Radiance, is translated into Radiance camera information, and these images are created. And these are the two Revit models, which two different views. And once we have run the model in prototype, the views are created, and on A and C here they are Revit models, view of the Revit models, and B and D are the RView generated images of the Radiance model, Radiance input file which was created. We could see that the geometry as well as material got translated accurately, and the results are also written to the project file. Wherever we create the Revit file, the results are written in the directory. A hierarchy is there, a project structure is there, they get written. So the first image is a human sensitive image, and the second one is a false color image, and third one is an ISO contour image. So what we have seen is like this tool could be used very easily for performing daylight simulation and just making the model. All that Architec has to do is just make the model and load the programs. It could be icons also on the ribbon, and click them. And automatically, once you place the sensor points and the cameras, where you want the what view you want, the prototype does it. And if at all there is any changes, that is for the Architec. Architec can easily do the simulation, and the results are generated. But if a simulation expert is using this tool, he can look into the Radiance input file. They have the ASCII files which are there in the project directory. They can open. One who has knowledge about Radiance input file, he can tweak some values like rendering settings. So, and he can run it. However, if the geometry is changed, then we have to perform the simulation again. But even that also is fairly easy. So this. So finally, I want to conclude that this tool is very easy for the students as well as architects to do the daylighting analysis of their project. And I just want to say that this thesis, the prototype has been developed as a part of my thesis in Texas A&M, and it is also a part of a National Science Foundation called a research project called Physical Building Information Modeling. One of the part of this project is integrating BIM with energy simulation tools, and I have done the second part where we have integrated BIM with daylight simulation tools. And I want to acknowledge my advisors also, Dr. Jeff Habrel and Mark Clayton and Vayan, who have guided me. With this, I'll conclude my presentation. Thank you so much.
Thank you, Mr. Sandeep.
Yes.
We can now move on to the questions part. I will first start with Professor Salih Ofluoğlu. How much the design decisions regarding HVAC systems and photovoltaics taken in the early design stages change in the later stages of a project?
Photovoltaics are considered at early phases for measuring whether students' initial objectives for energy use can be fulfilled. And we mainly focus on early design, so we don't have much elaboration or exploration on those issues. We focus whether the energy objective can be fulfilled with energy creation on the site.
Thank you. And another question is to Milad. Can you please turn on your microphone, Milad? And Salih, could you please start it up? Thank you.
Sure.
Are you planning to go global with your measurement and verification program? If so, when would you do it?
Well, yes, because it's already a commercial product. We have plans to go globally in the next year, 2021. And in 2020, we're actually installing our platform all across Canada.
One other question is, since the measurement and verification is an ongoing process, how do you define the duration of your contract with your clients?
Well, that's actually a very nice question. As M&V process in a continuous measurement and verification, it means that at the end of our project, whenever we do our commissioning and we do our analysis, we'll leave the platform at the side of the project, so it actually does this monitoring and measurement and verification throughout the entire life cycle of a building. So that is that is the value that comes from the real-time actually monitoring. But to answer your question about the duration of the project itself, so it depends on the complexity of the building, and based on the complexity and number of data points that comes from the building management system, the duration is different. But at the end of the project, the M&V will continue its job and will be actually left in the building.
Okay, perfect. It's a general question. The advantages of BIM has mentioned, but nothing is perfect, and BIM has its downsides. What do you think BIM needs to improve or are still missing? Who would like to answer? Sandeep, would you like, or Salih, would you like to?
I think it's the turn of Sandeep.
Okay, perfect.
Yes. BIM has the geometry information, but it doesn't have information. There are several performance analysis which we can do, but the BIM doesn't have all the information which is necessary for each performance analysis. For example, in my case, it has RGB values, which could be converted into radiance reflectance values using a brightness formula. However, we don't have a specularity information as well as roughness information which the radians need to do the simulation. So those have to be added. Like there is a need to collect the information, what kind of parameters are necessary, and BIM vendors can add those in the future. Like in this kind of projects, we can write to them that we use the BIM modeling tools to do the building performance analysis, but your BIM modeling tool is not providing these values. Could you address this and add it in the future releases? So I would say.
Okay, thank you. Yes, Salih, Ofluoğlu professor, please.
In our case, we had a problem. That is the problem, lack of standardization between BIM software and analysis tools. This year we introduced a new product, let me name it Trimble Safira, to compare it with our existing pipeline product, that is Insight 360. The same materials, the same site conditions really produced much more different results. Insight had, if I'm not wrong, Energy Plus GOE2 combination. Safari had Energy Plus, but the results were completely different, and students were really puzzled how it could be. And apart from it, we also need local data related to energy use by building types. That's another story, but basically we are using the United States data in our courses. We are in much need of Turkish data for our courses.
Good points, thank you. And one more question. Sorry.
I just wanted to add on to something Professor Salih has said, that whenever we are using tools, a lot of times the parameter settings are not spelled out. So you really have to dig deep into what are the settings. Like when we were developing this tool, I went to Radiance literature, and there were a lot of parameter values which are there on the Radiance website, and some are gives you a quick simulation, but the results are crude, and some are very accurate. So whenever we purchase the software, we really don't see that, and we really need to probe. And when the parameters, the simulation under the hood, the simulation engine is same, but if the parameters change, the values change. So it has a huge impact on it. Yeah. Yes.
Would you like to add something more to add on? Mr. Salih. Okay. One more question. And at which stages of the design to do energy analysis? Because the orientation of the building has a different effect. The installation is different. Maybe it would be good if the question asker could re-ask it again, because the installation part is not very clear, but I think it's trying to say that maybe before the building mass design, we should start the energy analysis. This is the point of the presentation of Professor Salih, that he was also talking about the early stages. As far as I'm concerned, just before deciding the form of the building, we should start the energy analysis, as it has a huge impact. But if anyone would like to add something, I would be very pleased.
Well, what I'm understanding from the question is that maybe the person who is asking wanted to know the orientation, because the orientation does have a lot of effect. And whenever you are deciding on the radiation analysis, we had to do it in that is the first step. I've been teaching one course and in my university, and the first step is the orientation and the radiation analysis, because it has a huge impact on the rest of the things. So we have to, sometimes the orientation is optimized for solar, and sometimes the orientation is optimized for the wind also. You have to take a call. I mean, that's my answer for that question.
How much do you think, is there a number that defines the magnitude of the energy saving that could be brought by changing the orientation? Is there this kind of statistics or something?
I don't have a number, but if I mean, we all know from the literature that elongated building has to face north and south. But if you tilt, it just causes so much of heat gain from the east and the west, and you cannot shade it. So I don't have a number, but we had to be very careful in the orientation. Yeah.
I can add to that question for the first part, at which stages of the design to the energy analysis. According to BIM implementation guides, it has to be conducted every phases of design. So you have to verify your initial design decisions with detailed material attributes later in the design process.
Okay. Thank you. I think we're done with all the questions. I would be very pleased if you have some points to share just before leaving, closing the session.
Thank you for the great moderation.
Thank you very much. It was a great session. It was a great opportunity for me to discuss with you all the details.
In fact, I worked with my professor, and he is an expert in MNV, Jeff Hablel at Texas A&M. So he teaches a class, and it's somewhat a Greek and Latin for me, but it is one of the important steps. I really enjoyed watching the tool and also Professor Salih's presentation. And I have one question I totally forgot to ask. So you are teaching this course at a master level or undergrad level?
Master's level.
Master's level.
Postgraduate.
Okay. What is the duration of the semester?
It's 14 weeks.
How many softwares they learn in this 14 weeks? Okay.
A lot of things they have to learn. That's one of the problem. You pinpoint one of the problem there. I think it would be. I sometimes think that it would be much beneficial if we could introduce it at undergraduate level as part of an integrated curriculum. But it's all another issue, and the academics and politics.
Thank you for answering. Yes, thank you. Thank you, Neil. It's a pleasure meeting you all.
Yeah, for me as well. It was a great pleasure. Very nice to meet you. Hope to see you and talk to you soon again.
Sure.
Session.
Yes.
Thank
you.